Hi everyone, so today I'm going to talk about this amazing algorithm called Topological Sort. It is an algorithm on graphs, and a lot of people asked me to talk about this in one of my Tech Toolbox videos. So the thing is, a lot of people think that it's difficult, and I think that's mostly because they don't really understand the concepts that well. But trust me, once you understand the concept and grasp it, it actually becomes fairly easy. The other thing is that on LeetCode, a lot of topological sort questions are marked as hard, and I think that just psychologically makes a lot of people think topological sort is a difficult algorithm. And I think it's also because a lot of people don't really get asked this question in interviews, and because it is so infrequently asked, it's labeled as hard. But again, I was asked topological sort in two of my interviews, and like I said, it's fairly easy. It is not hard at all. You just need to understand the concept. And in this video, I'm going to try my best to share with you how I understand what topological sort is, and hopefully it will become as easy to you as it is to me. So say we have a graph. So I have 5, 6, 3, 4, 6 also goes to 4, and then I have 0, I have 1, I have 2. This is in fact a very classic example which is used to show what topological sorting actually looks like. So what topological sort as an algorithm says is that we want to provide a partial ordering among the vertices of the graph such that if there is an edge from u to v, so where u and v are the vertices and the edge is denoted as like an arrow between u and v, then u is less than me, which means that u comes before v in the ordering. So what does that mean? So say 5 is my u and 3 is my v, and this is the edge that I'm talking about from u to v. When I write the solution for my topological sort, I'm going to write 5 comma 3 because 5 has come before v, 5 has come before 3, and this is how it will always stay in my topological sort. 3 should never come before 5. So if I had to write topological sort for say the entire graph, it would look something like this. So 5 has to come before both 3 and 4. So 5 has to come before 3 and 4, and I can write 3 and 4 together because they're on the same level. But as you can see, 6 also comes before, so maybe I can write 6 here. So 5, 6, 3, 4, and then as you can see, 0 and 1 should come after 3, so 0 comma 1, and then 2 also comes there, and then 1 comes after 4, and we've already covered 1. So yeah, this is one possible topological sort. Now there is a couple of things that you need to keep in mind. As you can see from the graph, this is a directed acyclic graph. What this means is that there are no cycles and it's directed. That means if there are two vertices u and v and there is an edge from u to v, then there can't be an edge from v to u. That's not acceptable. Then there are no cycles, and then as you can see, there can be multiple orderings for the same graph. So as you can see, if 3 and 4 are on the same level, if I write 4 before 3 or 3 before 4, it doesn't really matter. It is still a topological sorting. Now the other definition that I think is important to understand is that of a source, and that also brings us to the definition of a sink. So what source means is any vertex which has no incoming edge and only has outgoing edges. So for example, 5 here has no incoming edges, right, and only has outgoing edges. This is known as a source. And another way that we can call it is that its in degree is actually equal to 0. Similarly, sink is the exact opposite. It has incoming edges but has no outgoing edges. So this is called a sink, and its out degree is actually equal to 0. So we can say that a topological ordering starts with one of the sources and ends at one of the sinks. Now the easiest way, or one of the easiest ways to solve topological sort, is by traversing the graph in a breadth first search manner. So we can start with all of the sources. So for here, 5 is a source and 6 is a source. We can start with all the sources and then stepwise put all of the sources in a sorted list, and then we remove those sources. So if I start with 5 and 6, I can remove these, and then 3, 4, 0, 1, 2 becomes my next graph. Then once I've put 3 and 4 into the list, 0, 1, 2 becomes my graph, and then I can put those in the list. So if I had to do it in a stepwise fashion, I'm going to draw this out again. So I have 5, I have 6, I have 3, 4, 0, 1 and 2. Then the way that I had drawn the connection was 5 comes before 3 and 4, 6 comes before 4 and 2, and 3 goes to 0, 1 and 2, and then 4 goes only to 1. So what we're going to do is that we're going to check what all of the sources are. In this case, we can actually start with writing the in degrees, and so 0, 5 and 6 have in degrees of 0. So we put them into a sorted list, and then we remove these. So this is what our graph looks like now. We can also maybe imagine that 5 is gone, 6 is gone, and then these connections are gone. This is gone. And then what does my new source look like? So the next sources that I have are 3 and 4. The reason I'm not putting 2 is because 3 is still before 2. So now that I can remove 3 and I can remove 4 and I can remove all of these, so now all of these become my sources, and then I can just add them in any particular order that I want. And so 5, 6, 3, 4, 0, 1, 2. As I said, if I had wanted to write 5, 6, 3, 4, 1, 0, 2, that would also be valid. Similarly, 5, 6, 3, 4, 2, 1, 0, that would also be valid. If they're on the same level, they can be put in any particular ordering and it would all still be valid. Now, as you can imagine, the implementation of this is pretty straightforward once you know what the graph looks like. It is very easy to maybe have the graph as a dictionary. So maybe the graph is the vertex u to all of its v1, v2, v3 and so on, and then you calculate the in degrees of each vertex. As you can see, we always want to start with an in degree of 0. Now in case we don't find an in degree of 0 in the entire graph, that means we have a cycle, mostly because this is what something that it will look like. Because if there was not a cycle, at least one of them will have an in degree of 0. That means we can't do a topological sort. But once you found an in degree of 0, you can continuously go and decrease the in degrees of the remaining elements in the same way that we started removing the elements here. I can give you a quick short example. I'm going to draw the graph again. In hindsight, I should probably have copied the graph so that I didn't have to draw it out again and again, but it's okay. It's not a very big graph. So 5, 6, 3, 4, 0, 1, 2, 5 connects to 3, 5 connects to 4, 6 connects to 4, and 6 connects to 2, 3 connects to 0, 1, and 2, and then 4 connects to 1. What I was trying to say here was when you're trying to implement that, maybe you have this graph in the form of a dictionary, and then you calculate the in degrees of all of the vertices. So in degree is 0, in degree is 0, in degree is 1, and in degree is essentially the number of edges that are coming into the particular node. So for 4, the in degree is actually equal to 2. For 2, it's 1. For 1, it's 2, and for 0, it's 1. So what we are trying to do is that we start with anything that has an in degree of 0 and put it in the sorted list. So in this case, it's 5 and 6, and then we remove them from the graph. So once you remove them from the graph, what's going to happen is that the in degrees of the new nodes is going to change, right? So the in degree here is going to become 1, 0. Here also it's 0. Here it's 1. Here it's 2. Here it's 1. So the next elements basically that we put in are the elements with in degree zeros, 3 and 4, and then we cut them out and then we reduce these, and of course the in degrees are again going to reduce, and then you can put 0, 0, 0. Of course, I did them together. You will have to remove the vertices one by one when you're writing the code. So you'll have one vertex that possibly has an index in degree 0, one of them which has 1. You handle the case with the 0 first, and then you handle the case with the next minimum in degree, which happens to be 1, or this also might get reduced to 0. Essentially, it's very simple. The steps include initialization, where you store the graph as an adjacent list, which means you use a dictionary in Python. Then you build the graph and find the in degrees of all the vertices, find all the sources, and then keep sorting until you reach the end. The time complexity and space complexity is very simple, as we are going to traverse the entire graph from up here to down here. So we are traversing all of the, say, m vertices and n edges. So the complexity actually becomes O of m plus n, or you can say O of v plus e, because you're traversing every single edge and every single vertex and edge in the graph to be able to complete the ordering. And then as far as space complexity is concerned, you can say it's O of v, because that's what you're trying to make the list of all of the vertices. But then if you don't want to consider the output in the complexity, then the space complexity is just going to be O of 1. Thank you. We'll go over the implementation of this in another video, but I hope you're able to understand the concept behind topological sort, and I really hope this video was helpful.